Well, good morning, class. This is Mr. Roberts at Shasta High School, and today we are going to continue our talk. If you remember last Friday, we had looked at section 131, and the topic there was how can I rewrite it? And we investigated rewriting expressions with exponents. We are going to continue this conversation today in section 1.3.2. Again, the title also is How Can I Rewrite It? But you'll notice the subtitle now is Zero and Negative Exponents. So our goal for the day is to extend our work with dealing with exponents into the realm of what is a negative exponent, how do we deal with them, and what's a zero exponent. So this is kind of a decent summary problem from Friday. If I take a look at this, this exponent 3 is indicating to me that I am raising something to the third power, and it's this collection of factors, right? You can see I've got 3x squared. If I'm going to expand this, I would need to have exactly 3 of those 3x squareds. So to begin the process of simplifying this, I would go ahead and write out the fact that there are 3 of these 3x squared. So I could write 3x to the second times another 3x to the second times another 3x to the second. So you can see I have exactly 3 of these factor groupings, 3xx. In my denominator, I have 9x to the fifth power. And I actually am going to choose to rewrite the number 9 as I'll just write it as 3. And then I'll just go ahead and write this as x to the fifth. So these are equivalent to each other. And that's one of the things that I always try to train my eyes to do. I want my eyes to be able to look at this expression and just verify, yeah, there are 3 of the 3x squareds. 3x squared, 3x squared, 3x squared. And yes, 3 times 3 is 9, and this is x to the fifth. Because it's important as I move forward that what I've written down is equivalent to what I had. Now, if I move forward another step, right, I could choose to go ahead and write all these out. Each one of these x squareds contain 2 factors of x's. That's an x times another x. But I can also just count them. I have 1, 2, 3, 4, 5, 6. So I have 6 factors of x. So I could write this as 3, 3, 3. And then I could write it as x to the sixth power. And then on my denominator, I've got 3, 3. And I've got x to the fifth power. Now at this point we can already see a 1 that's lurking in here, right? Because these are factors, I have 3 times 3 over 3 times 3, so this is a giant 1. And because of that, because it equals 1, I can leave it here and not keep writing it forward because multiplication by 1 doesn't change anything. So because that equals the number 1, right, I can just proceed forward and I can go ahead and now just write that I'm going to have exactly a 3. And instead of x to the sixth, I'm going to write x to the fifth and then times another x. And in my denominator, I'm just going to write an x to the fifth because that's what's left. So notice the big difference I made here, right? First of all, the giant 1 is gone, and I'm left with this 6. And I've rewritten this as 5 factors of x tacked on with another single factor of x. So this is still 6 factors of x. But because I've written this out like this, I can very clearly see that this is equal to 1, and I'm left with just 3x. So if I come back and back all the way out of this original expression, 3x squared raised to the third power over 9x to the fifth is equivalent to 3x. And I think I think it's kind of clear why we would consider this a simplified version, right? This is fully simplified. There's no common factors in the numerator or denominator, and all of my bases are collected to just this single expression. Just to kind of get us warmed up, I'd appreciate if you just quickly jotted this down. Pause the video, and then we will verify if you did this correctly. So the solution should be, in my numerator, I had 2 factors of 3 and then the x squared. In the denominator, I've got the 3, 3, 3, and then there's an x to the fourth. And you can see the way that I've grouped this together, and I'm left with a single factor of 1 in the numerator, and my denominator is 3x squared. And I think that we're going to do this set as well. So there are 6 additional problems here. This will really aid our conversation today. If you go ahead and take a moment, pause the video, and simplify each of these. Specifically, I want you to focus on what we talked about in class and online Friday and rewrite each of these expressions as simply as possible. If you please, as you're doing this, kind of look for patterns, or maybe you know a shortcut. And if that's the case, right, I want you to think about those things because we're going to talk about those in just a moment. Okay, so let's check these and think about some of our reasoning for them. So in this first expression, we have a total of 7 factors of x, and then you can see that we are multiplying, right? Oh, it's implicit here with even without the dot. We're multiplying by an additional 4 factors of x. So when we're done, the question is how many factors of x we have. We are at 7, 8, 9, 10, 11. So there are a total of 11 factors of x. So this is x to the 11th power. In the next expression, I have 3 of these x cubes, right? So this is, if I wanted to write it out, there's an x cubed times another x cubed times another x cubed. And if I count these factors of x up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have x to the 9th power. In the following expression, I've got a numerator that has 14 factors of x, and I have a denominator that has 2. I'm sorry, and it's not x, this is m. So I could break up these factors of m in the numerator and write it as m to the 12th times m to the 2nd. And when I do that, right, it's very clear that I have liberated 2 factors of m. And I can, at this point, not write that down anymore, and this just simply becomes m to the 12th power. And I think probably many of you are saying, yeah, that's the difference between the numerator and the denominator's exponents, right? 14 minus 2 is 12. Let's go down to this one. This one has 4 of these, and if I wrote it out, it would be, x squared, y squared, x squared, y squared, x squared, y squared, x squared, y squared. But every single time I wrote down the x squared, it would be 2 more factors of x. In fact, I would have 1, 2, 3, 4, 5, 6, 7, 8. I would have 8 factors of x because I have exactly 4 of these groupings. Well, probably a shortcut would be this is x to the 8th power times y to the 8th power. And if you want, you can verify this by writing out the 4 factors of x squared, y squared, and then counting the fact that, yeah, there really are 8 factors of x there. The next problem over, we have 5 factors of x in the numerator and 2 factors of x in the denominator. And if I thought it out, just the x's, right, I know for a fact that 3 of those would group up with 2 of these. I'm sorry, 2 of these. I would be left over with 3. 2 of the factors of x here, right? This is x, 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 x. 2 of them could group up with these 2 and form a giant one, and I would be left with just the difference here, right? I'd be left with 3 of those. So this is going to be x to the 3rd. And same thing happens with the y's, right? I've got 11 of the groupings of y factor, 11 y factors. And when I divide that by 3 factors of y, the difference between these is what I care about, which would be 8. So 8 is 11 minus 3. And then on the final expression, in my denominator, I have 3 factors of 2. 8 is 2, 2, 2. I have a single factor of 2 in the numerator. So you can see that this becomes 1 over 4. Yeah, and 2/8 reduces to 1/4 as a fraction. And then I've got these, I could break up the 12 factors of x's. 10 of them times 2 more, so that's 12 factors of x over 2 factors of x. So that's a total of 10 that are left over after that 1 is gone. So this one the answer here would be x to the 10th over 4. X to the 10th, whoops, not to the 2nd, x to the 10th over 4. So for this problem, I want us to get this table written into our notes. And the instructions were, it says, use the table below, summarize the patterns you found in those exercises that we just did. And if I just zoom in, I'm just going to put this here, right? So in your table, I want you to have both this expression. I would like for you to have the generalization and these descriptions of why it's true. So on the first one, when I've got 25 factors of x and I multiply by 40 more factors of x, that's a combined grouping of 65 factors of x. It becomes x to the 65th. And then my generalization is when my bases are the same, right? When they're identical numbers, in this case both x, and I'm raising 1 to the m and 1 to the n, and m and n could be the same number. I just end up adding those, right? Because I'm bringing in additional factors. So, and for why this is true, I just said we are increasing the number of factors. Where we've got 25 of them and we're increasing it by 40 more factors. We've got m factors and we're increasing that by n more factors. The next one, it says x to the 36th over x to the 13th. That ends up being the difference in those factors. If I was to write all those out, 36 factors of x over 13 factors of x, 13 of those factors of x below would group up with 13 above, and I would be left with a difference of 23. So you can see, I just wrote down, we are decreasing the number of factors. So I've got m of them over x to the n of them, and I just take m and I subtract n. And then the final one here, this is kind of like, it goes back to basically what multiplication is. I have 12 of the x to the fifths. If I wrote out 12 of them and counted them, I would see that each one of those fives, if I had 12 of those 5 factors groupings, it would get a total of 60 factors of x. So if I have a power x to the m and I'm raising it to the nth power, that's the same as x to the m times m times n. And I wrote down here that we have n groups of factors, and each group has m factors in it. So that's why we are multiplying there. So I think the use of those 3 facts alone could expedite a lot of our work in terms of working with exponents. So we're going to extend this by 2 more facts, hopefully by the end of this session. We're right now at 12 minutes, so we got to wrap up in about 8. So to help us continue in our investigation here, I'm asking that we rewrite the following 3 expressions 2 times. Once using repeated multiplication and the giant ones, and then another time using the rules that we just developed above. So I'm actually going to do these with you, so I want you to just follow along and make sure you get these in your notes. So if I was to do this expression in terms of a giant 1, I would just write the numerator is x to the 4th again. In my denominator, I would have x to the 4th, and then I would have times an x to the 1st power, or I could just write it with the x with no exponent. So this simplification, right, this is 1, and I'm left with what? In the numerator, I have the number 1, and in the denominator, I have x to the 1st power, right? X to the 1st. Now, if I was to do this using the simplification rules above, right, which was, we wrote this as if you have, I can't remember the letters we used above, but I'll just say if you have x to the m over x to the n, this is going to become x to the m minus n. Well, in this case, x is my base, right? So I'll write x again. My numerator is 4, that's the m, minus 5. And you can see that I end up getting x to the negative 1st power. This is exactly what I wanted to tease out here. This idea that x to the negative 1 is the same as 1 over x to the positive 1, right, is a very important observation. This is true whenever we have a negative exponent, right? Really, when we have a negative exponent, what we have is a reciprocal. And it doesn't matter if my exponent is to the negative 1 or to the negative 3rd. This expression, x to the negative 1, is equivalent to 1 over x to the 1st power. Let's take a look at the next one. Same thing, using the giant ones. In the numerator, I've got x squared, and then my denominator, I've got x squared times another x squared. These group, and I'm left with, in the numerator, just the 1, and in the denominator, x squared. So, and if I do this with the simplification rules, this becomes x to the 2 minus 4, which is x to the negative second power. So here's our second example of this. X to the negative second, right, is 1 over x to the second. Again, we're looking at the fact that a negative exponent is just indicating that it's actually just a reciprocal, or you can think we're dividing by x squared. And then our third example here is I've got x to the 7th over x to the 10th. As a giant one, we're looking at, as a giant one, we're looking at a denominator. I'll rewrite this as x to the 7th times x to the 3rd. That is exactly 10 factors of x, which matches my numerator. And I've got x to the 7th power in the numerator. There's the giant one. So we are left with x to the 3rd in my denominator. Remember, this is a 1. I'm the one who almost forgot. And then if I do this using the rule, right, this is x to the 7 minus 10, which is x to the negative 3rd. Again, this is nice because we can, if we forget this, right, we can just come up with a couple examples like this, write things down two ways, right? Write it using this idea about creating the number 1 and identifying the giant ones, and then also using this rule, and then that gives us an entry point into what does it mean to have a negative exponent. And another, I guess, a piece of low-hanging fruit. This is something that we can kind of get for easy. We can get easily from where we're at mentally right now. Is this idea that I want to share with you now? So what we've been doing is writing these things down in two different ways. Once using our rules for exponents, right, that we looked at and observed above and wrote down in the table, and the other way using this idea of the giant one. Well, if I was to think about this in terms of a giant one, right, x to the m over x to the m, I have exactly m factors of x in both the numerator and denominator. That is 1, right? So this thing is equal to the number 1. And then if I look at it in terms of my exponent rules, this is going to be x to the this m, right? M minus this m. Well, and m minus itself is 0, so this is going to become x to the 0 power. So this is a great result, right? If we end up getting something to the 0 power, right, we know that that equals the number 1. And so now that we're at it, I'd like for us to include these two additional facts, right? If I have a 0 exponent, right, when I have something raised to the 0 power, we know that that's going to equal 1 for all values of x that are not 0, right? If x is 0, that's a problem for us. But as long as x isn't 0, as long as the base isn't 0, anything to the 0 power equals 1. And this other idea is that what is a negative exponent? It's nothing more than a reciprocal. So if I have x to the negative second, it's 1 over x. If I have x to the negative fifth, it's 1 over x to the fifth. In fact, probably a better general form of this would be x to the negative a power is, or opposite of a, is the same as 1 over x to the a power. All right, let's finish up with one more idea. So this problem is one that you'll probably want to maybe watch more than once right here and contemplate what I'm saying. This is a technique that we'll use a lot when we're dealing with negative exponents. So the instructions for this problem are, I would like for you to expand as needed in order to use the giant one to rewrite each expression below without any negative exponents. So we're going to be simplifying this up and we're going to be removing negative exponents. So as I look at it, I can see my numerator, it's a multiplication problem, right? I've got a fraction times another fraction. This first fraction's numerator is 15 and times 1. So if I was to bring those together, that would just be 15. 15 times 1 is 1. And in my denominator, I've got x squared times 45 times x to the negative third. Well, I can combine that. I can write this as, I'd write the 45 in the front, and then I'll just go ahead and write x squared times x to the negative third. So again, just numerator times numerator, denominator times denominator, and then I did I switched the x squared and 45 so that this coefficient's in front. If I look at this denominator, right, when I look at the negative or x squared times x to the negative third, I know that I could combine these by adding 2 and negative 3. So I can rewrite this as 15, I'll write 15 in the numerator, over 45 times x to the negative first power, because 2 plus negative 3 is negative 1. So I've got x to the negative first. For sure, there's something that we can do with the 15s as well. 45 is actually 3 times 15. 30, 40, it is. So I can rewrite this as 15 in my numerator times a 3 times a 15 in the denominator times x to the negative first power, and this can go away. So what I am left with is a numerator with a 1 and a denominator with 3x to the negative first power. So I think most of this so far has been pretty straightforward, but the instructions I gave verbally at the start was I wanted us to also write it without negative exponents. So the problem I have right now is, how do I deal with the fact that in my denominator I have x to the negative 1? And this is the technique that we'll use. I can always multiply by the number 1. If I multiply by the number 1, I don't change a thing. So if I want to, I can multiply by the number 1 in the form of x over x. And the reason why I selected x over x is because this negative 1 and this x to the positive 1, when I combine those, become x to the 0 power, and x to the 0 power equals the number 1. And so those two things together, right, these two things together equal x to the 0, which is 1. So by introducing this giant 1 here, right, by introducing this giant 1, oops, I wanted to get a different pen color. By introducing this giant 1, right, I'm able to cancel out a 1 that becomes part of my denominator. So if I was writing this out, I would write exactly what I wrote there, and then the next thing I would write is, perhaps I might write the numerator is now x, the denominator is now 3, and then x to the 0, and then I might take this one step further and write, oh, this is just x over the number 3. So this simplifies to x over 3, and if we back all the way out, right, we're saying that this expression is simply x thirds, x over 3. So this technique, specifically what happened right here, is the thing that we'll be seeing more of tomorrow, and we'll be practicing. All right, so I've gone a little bit over. Thank you very much. I look forward to seeing you that are away today, tomorrow in class. This is Mr. Roberts. Goodbye.